Okay, so then we're talking about this kind of general way of representing networks. We've got the width of the network, the depth of the network, and so we talk about deep learning. We're talking about increasing the number of hidden layers, right? So there's this, I was showing it as the universal approximation theorem yesterday. They have a slightly different form of it, but basically saying that even a single hidden layer is good enough to represent any function. But they did add this thing that I was missing yesterday, which is good to point out. You can represent any function if you write down the weights, but can you learn it? Some of them are not learnable, like we showed with the XOR one. That can't be learned directly. But you could write it down. It's just that it's not something you get to by following some kind of gradient. But to make that better, we can basically increase the depth. So how does depth help? So depth basically gives you more opportunities to model the function in independent ways. That's how I think of it. Because the number of units you'd need with a single layer could be just very, very large. What you basically do is once you start adding more hidden units, right? And so maybe, here we've got 2 hidden units in our model, but maybe we're going to have more of them, right? As you add more hidden units, you're basically saying, give me the ability to do another fold in the data. Because every one of these has, a whole bunch of weights and a whole bunch of like hidden units that's going to have fully connected on the data, and then you get another chance to try that. So they're all independent, right? So you've got a whole bunch of these weights that are like separately independently combining every one of the input features into something on the output, right? But they're done in parallel, right? And so when you get the second layer now, you've got, let's say, 2, you've got a bunch of more weights. These ones can get another pass at independently cutting up what the output of the previous layer was. So the figure here, they're talking about this folds. I always use this one. If you think of it like folding paper, the first paper you can draw as complex a line as you want with a single layer to basically divide the points. But maybe you still can't get all of them because you don't want to have, well, you could, right? Let's say you draw some line on it, right? And then you fold the paper again and you say, okay, now that you folded the paper, you can draw another line over the points from this different perspective, given with the previous line kind of included. It's essentially like learning an embedding, right? We talked about PCA and TSNE and all these things. The first layer essentially learned its own embedding, but it was kind of more unrestricted. So every fold of the paper is like adding another hidden layer, and basically by looking through all the folds and the previous projections, you can now draw more lines. So why is this a benefit, right? Because you can draw any complex line on that single sheet of paper, technically. But how complicated is that line going to be, right? Lots of curves and wiggles and really particular points, right? That's the definition of overfitting. That's the definition of something that could easily be wrong because one little line's wrong. It's much nicer to say, wouldn't you prefer to have each of the lines here essentially be something very simple, right? And then you've got a bunch of simpler lines, but you get to overlap them on top of each other, right? And so when you basically are doing deep learning, it allows you to say that the functions being learned by each hidden layer can be simpler, more robust, and more general. So that's the intuition for how it works. They didn't know that when they were doing it. They basically were hacking different things and trying it out, and eventually saw that, wow, if we add like 5 layers, it's really great. Once we figured out how to make it work, right? So they've got some results on like, I don't know, some very general data set that they're using here. To say that, add more layers, then you can generalize the data better, right? So remember what generalization means? Have we really even defined that? If this were in physical class, I would ask from the audience, but I don't think I will today. If you want to chime in with things, feel free, especially if you have questions. Right, generalization is kind of the reverse of overfitting, right? If we, I had a slide of that somewhere. When you do things on your test set, right? So the whole idea that we have a training set and a test set is to basically encourage our evaluation to take generalization into account, right? Because you're going to test your model on something you've never seen before. And so if it generalizes well, it should do well on the test data, right? If it's overfitting, then it will not do well on test data because it only knows how to do well on things it's explicitly seen, right? And so they find that as you have deeper models, the generalization improves, right? So basically the models get better and better on the test set, even if they don't necessarily get better on the training set. And so part of this is the number of parameters, right? So as you add more layers, add more weights and layers, you're going to have more parameters. But it's not just that, right? Because you can have a fully connected, simple model, which works, fairly well. These are all above 90% accuracy. And what are we talking about here? So here they're comparing convolutional neural networks with fully connected. So right now we're talking about fully connected. Do we have there's nothing in this slide deck talking about what fully connected or convolutional means, but I'll show you that. The main point from this figure is showing that the fully connected one's accuracy is going down, basically, or plateauing. Even as the number of parameters increases, it's not getting any better, right? Whereas these other models that are deep, okay, that's what they're showing. This one is a short model, it's only 3 deep, but it's using this convolutional trick. And it does well for a while, and then it starts doing worse again, right, on the test set. So its basic generalization is kind of peaked out at this point. Whereas this one that's deeper with 11 layers keeps getting better, right? And so you could have a similar model, similar graph, just with fully connected ones, and that would be more interesting here. But what do they mean by fully connected versus not fully connected? Because I guess at the moment we haven't really given the idea of what that could be. So this is kind of a preview of, well, there's 2 different reasons to do it. Right, so we have our inputs, we have some hidden nodes, however many there are. Say this is n for the data. I have a second layer. Guess we need to have one for every layer. Right, when I say fully connected, we're assuming that every node in the previous layer is connected to every node in the next layer, right? And that's the default way that neural networks work, right? But it's not necessary, right? You could say that only some of these are represented, right? So we could get rid of some of those and just not have them. And then we'd have a more sparse network, right? But the question is, how do you choose which ones are going to be connected and which ones are not going to be connected? There's no reason to do it one way or another when you're doing it this way. So a CNN, which has this convolutional property, I don't know if you can see that well enough. Let's make it bigger. Hopefully people can see that one, other than reading my handwriting. It explicitly does some tricks that says, how how does it work? Every node essentially in the previous layer, we'll just have I, connects to a bunch of nodes in the prior layer, but not all of them. All right, so we could have I and j, and so we'll say this node here, sorry, I'm just thinking it through as I'm thinking about it, will only connect to some of them, right? Basically by a neighborhood, right? So you could have that the prior node, I'm sorry, the hidden node in the next layer connects to just some of these ones, but then the other ones, there isn't any link, right? So maybe the other, this one is connecting, sorry, the next node over, it's connecting just to these three nodes, but not to the other ones, right? So you could have a local structure that doesn't really have full connection, where everything in the previous layer connects to everything in the next layer. And in images, this makes sense because what you're trying to do is say, okay, we've got an explicit thing here, and I only want to basically take the inputs from the pixels that are near me, right? And that's essentially what you do in a CNN. You say, my neighbors from the previous layer are going to be the nodes that carry data from pixels near me and not from ones that are far away, right? In a fully connected data set where we have a bunch of numbers, we don't know what they mean, there's no reason to do this. So that's the difference between kind of fully connected and for lack of a better word, not fully connected. So when we say it's not fully connected, we'll always have a particular way that it's not fully connected. This convolutional way is the main, most popular one. But we'll see that there's actually a way of improving just the performance of usual neural networks that also takes advantage of this lack of full connections. So you can look through the textbook's kind of version of backpropagation as well. It's pretty much the same, essentially just applying this chain rule that gets you from X to Z, from the inputs to the outputs, knowing that every step along the way you define things in a way that can be computed as a partial derivative. And so you kind of just methodically break them apart until you have them all. An important part of it, I guess I didn't mention yesterday, is that you're doing dynamic programming as you're computing this. So backpropagation algorithm computes these derivatives as it's going, but if it ever has to recompute the same one, because it's parallel, it's hit that node already in its calculations, it just caches it, right? So there's a lot of information that gets computed redundantly. And part of this, the reason this works, this is why GPUs are so useful, because GPUs can do these things in parallel and cache them, and then you don't have to come back and do it again. So the fact that all of these components can be done independently, at least in each layer, is part of the reason it can be computed on GPUs, because GPU is just a matrix computation chip, right, that does linear algebra really quickly and lots of parallel versions of the chip. So that can help a lot. And then they have a bunch of other graphs for showing how their graph notation kind of works together. I'm not going to be using it in a lot of detail, but it's something to refer to if you want to talk about a particular structure, of the of your network. So logistic regression that we talked about before, you're taking your inputs and your weights and your bias and computing some output, and this sigmoid function, which does that nonlinearity, is in there as the activation function there. So you can represent any network this way. They even have somewhere where you can represent SVMs that way. I don't want to do that one. But the general form of your neural network, then using their notation, comes out like this, where you've got your input data, and at every one of these steps you've got the activation function, some hidden unit, and then various kind of different paths I don't actually know what they're getting at here, so I'd have to look at their book to see what this network is coming from. And you got your loss function, which is your j that you're computing because you want to reduce the error, and that cross entropy term where you do the expected negative log. That's how the training comes. I don't know what they're doing here. I'd have to check what that was in their book. They have a bunch of other outputs. I don't know. Okay. See if I can just find that figure quickly, and I might just explain it. Oh, there we go. Oh, weight loss decay. Okay. So they have some kind of decaying weight loss. Okay, so this actually relates to the next topic. We're talking about regularization. So I guess in their version here, then they try, because the next thing about this is that just training them this way, there's lots of drawbacks. So you have to do things to basically stop it from overfitting, right? So neural networks are very good at overfitting because we have, of course, you know, a lot of weights, right, that we can use to fit something. And so one of the things you're trying to do then a lot of the time is to reduce the amount of overfitting. So one way you can do that is basically to add some decay terms. So what we're talking about in general is this concept of regularization, where you've got your basically your main function, the error you're trying to fit, and this is your loss function j, and that's your standard neural network basically. And then you say, let's try to make it not overfit too much. So there's lots of different ways you could do this, right? You can basically add some cost to basically say that the weights shouldn't be, you know, too high, or the weights should be more similar to each other, or whatever function you want to basically impose on it. So in this case, they're doing a adding a cost, right? So remember, we're trying to maximize the probability here of these outputs, but it's been put in that negative form. So we're representing this loss function, so we're going to minimize this cost that we've defined. And so if you want to basically say having your weights be too large is bad. You want to have more. If you want to have a more sparse network and more zeros or more very small weights, so that they're not trying to build something very complicated, you could add in these extra terms to try to minimize that. So the simplest way to do that is to add this kind of weighted lambda regularization term. And in this case, we're just taking the squares of the weight. So every weight value that you have, whatever it is, you're going to square it and add those together, right? So big weights are going to have a huge impact, and you'd rather your weights be smaller or even zero, right? And then you want to have some term that weights how important this is, right? And so you can basically decay that that lambda over time so that it has less impact. I think you want to increase it so that you basically freeze it, but that's what they're showing in this figure here. Is basically the network that has that term included would have this, but I guess the fundamental network that we're talking about wouldn't even have all these extra branches. So this is all, these figures are all coming from this chapter 6 in the deep learning textbook. So they correspond to the figures in that book. So you can kind of look there for the extra kind of background of it. And then if there's questions, we can kind of go into it kind of over time, right? Which is my other slide deck, which gets to this then.